In fifth grade, we look at the four spheres that interact in our environment. One is the geosphere, geo, earth, so we look at the land. The second is hydrosphere, water. We look at the water on our planet. And then we look at the atmosphere. And the atmosphere is interesting because it really connects the hydrosphere, the water, to the land. And then we have the biosphere, the living things on our planet. And so all of these spheres are interconnected. We've been spending some time looking at water, and now we're looking at air and some properties of air. And it's really helpful for kids to think about air as being made of particles. And when there's high pressure, there's a lot of particles packed together. When there's low pressure, the particles are stretched further apart. So we're going to do a variety of demonstrations. I'm only going to show you a few because I don't have time to show them all. Let me make sure this is working. Yeah. So I don't have time to show them all, but I want to show a few that are really kind of fun. One is a couple of plates here. And with this, I have a kid sit on the floor. They put their feet out. They pretend they're a race car driver. I make them say vroom, vroom. And then I pull them across the floor using this. And what this is, it's two plates. And there's a hole here connected to the pipe. And so when I put them together, I can lift up like this and they come apart easily. But if I suck on this end, and tighten the valve, then they do not come apart. And no matter how hard I pull, I can't pull them apart. And so I'll drag a kid across the floor with this. Another thing I do is I show them a bottle like this, and I have a balloon here, and I blow into it. And I can't inflate the balloon. So we talk about why, and the kids come up with this idea that there's already air in the bottle and I can't put any more air into the bottle unless this air can get out. And then I tell them, well, look, I have a hole here. So I cut a hole right there. And so now with the hole there, and I could show them that the air comes out. Maybe, I don't know if this will work, but you can see it blew that away. So I can blow this up, and then I can put my finger over the end. And now kids can see something that no child has ever seen before, and that's the inside of a balloon. But what's holding this open? And we can use this idea of particles to explain why this is held open. The particles in here are really packed and they're pushing in there. The particles out here are not as packed. There's low pressure here, high pressure here. Air always goes from high pressure to low pressure, and so the balloon stays open. Now, balloons are elastic. That's a property of them. They have this sort of elastic potential energy. And so this balloon is stretched, and it wants to go back to its original shape, but it can't. Because to go back to its original shape, it would have to stretch the air particles here, and they're not going to stretch because there's a lot of air particles pushing in over here. So if I let go, though, then you can see the air pressure here is equal to the air pressure here, and then the balloon just deflates. So that's one activity. Another one that we do is I have a feather and a penny in a vacuum chamber. If I go like this, you can see the feather floating down. And if I turn it up like this, you can see the feather floating down. And the feather goes a lot slower than the penny. And a lot of kids think that it's because the feather is lighter than the penny. And so what I do is I give them a couple of sheets of paper like this. I'll hold up 2 sheets of paper and I'll say, crumple one up. So I have a kid crumple up one of the lab tracks, which is always a treat. So a kid crumples up a lab track, and I'll crumple one up, and I'll say, okay, now which one weighs more? And about 8 or 9 or 10 kids, sometimes half the class, will say that this weighs more than this. Now, I'm not sure if that's what they think or whether they just think that this one's going to hit the table first or what, but I'll say they weigh the same because they were originally the same size sheet of paper with the same printing on it and everything. But if I drop these, then this one hits the table first. And so the thinking behind this is that if air is made of particles, then yeah, I think it has something to do with the mass being, tighter together, 2 things being of equal size. like a ping pong ball and a golf ball, well, you get them moving the same speed. It's going to be a lot harder for air to stop the golf ball. But here we have two things that have the same mass, and really the difference is that this is being hit by so many more air particles. Okay, so many more air particles. And so it falls more slowly. And so that's kind of the big idea, is just to get an understanding of the particle nature of air. So here's this balloon, this penny and feather, and the feather's falling really slowly. And so we're going to take the particles, out. So I'm going to put the tube on the end here and turn this on and close this. And we're going to get the air out of this tube. Now, this also shows something that I think is really fascinating. It's what happens when air goes from high pressure to low pressure, and we'll see that too. But we're going to take the air out. It shouldn't take too long. It's working its way. And so then I'm going to close the valve and turn this off and disconnect this. And now you can see the feather and the penny. Oh, there's the feather. It's already down there. If I go like this, there's the feather. It's already down there. It's not wafting down anymore because there's very few particles to bump into. So it doesn't bump into as many particles, so it falls as fast as the feather. Now, this is really low pressure. This might be the kind of pressure that would be way up in the atmosphere, 15,000 feet up, 20,000 feet up. Not very much air up there. If I was to open this up, you would see and hear the air rushing in. And way up here where it's clear, you're going to get condensation. Because when you think about it, when air goes from high pressure down at Earth's surface and gets pushed up by a mountain, now that's an example of the atmosphere interacting with the geosphere, but the air gets pushed up by a mountain. As the air rises, it has less pressure, it cools, and condensation happens, and you get a cloud forming. So we're going to see a little bit of condensation at the top here. But let me open this up and watch. And then if I look right here, you can see the condensation at the top. And so, it's kind of an interesting demo, and it's all disappeared now. It's evaporated again. But you see some condensation up there, which is evidence that there's water in air. That air has moisture, and that moisture can come out of the air. And that's an important idea for kids to understand, because we want them to see that the atmosphere is really sort of the connector between the hydrosphere and the geosphere. Water evaporates, it gets moved around by our atmosphere, it might fall as snow in the mountains and then run off, and then that runoff causes erosion and flows back down to the ocean, moving sediments. And so there's a lot going on and a lot of interactions between the atmosphere and the hydrosphere, the atmosphere, and the geosphere, which in turn affects the biosphere. For example, the winds rise up, we get rain on the Sierra Nevadas, on the western slopes of the Sierra Nevadas. But as soon as the air goes over the top and it's no longer rising, it starts to fall, it warms, and we don't get rain on the other side. And so you can see dramatic changes in vegetation. Anybody who's driven to Reno, they go up through the Sierras and it's all pine trees, and then you come over the summit and it's desolate. And you can do the same thing over Monitor Pass and many of the other passes in the Sierra Nevadas. So the last thing I wanted to show you that we did with the kids, again, this is just a partial summary of some of the things we did in our air pressure demos, this is a marshmallow. It's a large marshmallow, but it's a marshmallow, and we talk about how marshmallows are made of sugar and gelatin and, well, a lot of air. It's kind of a way to get rich in this world. If you can sell air and water, you're going to make a lot of money. So anyway, marshmallows are puffy. They're full of air. And when I put it in this jar, and this jar is sort of a real cheap way to make a vacuum chamber. It's an old spaghetti jar, and I just put a top on it. So here, I'm going to suck the air out. So right now, there's kind of an equilibrium. There's bubbles in the marshmallow, and they have a certain pressure, and there's a certain pressure outside, and they're kind of the same. So everything is the same. The marshmallow pretty much stays that size. But when I take the air out, what you're going to notice is that the marshmallow, the particles inside the marshmallow are not getting pushed and squeezed by the air pressure as much, so they can expand. And when the volume expands, the pressure goes down. So when the volume gets bigger, pressure goes down. And so the marshmallows are going to expand, and then they're going to give up their air. And at some point, the elasticity of the gelatin and the lack of air in the marshmallows are going to shrink back down to their original size. And then we have low pressure inside the marshmallow, low pressure outside the marshmallow. Then I'm going to suddenly put the air pressure back in. I'm going to put the air back in, and we're going to have high pressure in the jar, but the inside of the marshmallow is going to have low pressure. And let's watch what happens. So we turn this on, and you can see the marshmallow is growing, and then it pops and it gets smaller. And so now the marshmallow is pretty much back to its original size. Okay, pretty much back to its original size. And then I'm going to turn this off, and I'm going to let the air back in, and watch what happens. The marshmallow shrinks. It gets crushed by the air. And now the marshmallow comes out, and it's all wrinkly, which is another really fascinating thing, because we had a surface area on the outside of the marshmallow, and suddenly the volume gets smaller, so that surface area has to wrinkle to make up for the lack of volume. So there it is, and they're pretty tasty, kind of chewy, but very good.